Kia ora, Year 12. This question is a really good one on complex numbers that Sahisnu has sent me in tonight. And I'm going to do it in class, but I'm also making a video for you so that you can go over it thoroughly. It's just a little bit different, and you really have to think before you start kind of trying to move on to the next bit. So let's read it right through. First, we've got to solve an equation. Now, this is only worth 2 marks, right? It's an equation with with imaginary coefficient here. So it's not going to be one where the conjugate root theorem makes everything nice and easy. Z squared minus blah, blah, blah. I'm going to solve that by completing the square, or you can do quadratic formula. Both of them will work fine as usual. Next, we're told that in an Argon diagram with origin O, the roots of this equation are represented by the distinct points A and B. First, we're told that these two roots, A and B, lie on the imaginary axis. So we have to then find a relation between P and Q. So let's just visualize that right now. The imaginary axis is here. So the points might be, they could be here. I don't know, maybe they're both above 0, I. They could be here, they could be here, but the point is that they are separate points, right? And there are 2 of them. Then the next one is that given instead the triangle OAB is equilateral, we have to express Q in terms of P. So obviously doing this first part of the question right is crucial. So let's now just pause the video and try and complete the square on that expression and see how you go. So z squared minus 2 piz minus q is equal to 0. Z minus, so we're just going to halve the second term. So z minus pi squared. Now I have to take out the extra bit that I added in. So it's going to be minus p squared I squared minus q is equal to 0. Z minus pi squared is equal to q minus, hang on, let's go slowly on this. So this is plus p squared minus q is equal to 0. So this is now q minus p squared. Right, so we've got down to here okay. Now we have to just do the cleanup bit. So z is going to equal pi, oops, sorry guys, and I know I'm going slowly, but I think for most people in the class that's worthwhile. So we've got z is equal to pi plus or minus the square root of q minus p squared. And now we have to look at point A and point B. So point A represents the first root, which is z equals pi plus q minus p squared. And B is the negative root, negative one. So it's pi minus q minus p squared. Now just notice that they're not conjugates of each other because, as I said right at the start, the coefficients are not real. So if you're looking at that, now we can go to the second part of the question where it said that we've got these 2 roots and they're represented by the distinct points A and B. Given that A and B lie on the imaginary axis, find the link between P and Q. So let's look at A and B and just start by doing what I did when I didn't actually see this for about, I don't know, it was a good minute before I figured out my mistake. This is the real axis and this is the imaginary axis. So you might go, oh, yep, okay. That means that the real part of that number is 0. But if that's what I'm thinking, then, so if I go, okay, the real part must be 0, so q must equal p squared, then what that leaves me with is just, so if q equals p squared, we've got z is equal to pi for this one, but then we've got z is equal to pi for this one. So we're not getting distinct points. So that can't be the answer. So then we sit there and we kind of stare for a little bit. Let's think about what is going to give me 2 different numbers here and somewhere else. Well, that's going to happen if I have got p and then something else here that is actually an imaginary term, right? So what we've got to not assume is that this is real, right? So we don't know that. We don't know anything about q and p except that they are real numbers. Now, if I've got q minus p squared and that's a negative number, this is going to generate me something with I. So let's work that through. So point A, so if Q minus P squared is less than 0, what do we get? Well, we get Z is equal to PI plus, so we know that if Q minus P squared is negative, then P squared minus Q is positive. So we can rewrite this as negative P squared minus Q, which is PI plus, what am I doing? Root P squared minus QI. So that's my first root. And then for B, I'm going to get Z is equal to PI minus P squared minus QI. And that's going to generate me two distinct points. Okay, so my first point here and my second point here. Okay, so that's the second part of the question. We've got to find a relation between P and Q. I just need to make it even clearer what the condition is. So two distinct points on imaginary axis if Q minus P squared is a negative number. Okay, so that's that bit. Now, I think that's the hardest part of this question. I don't know what's going on with the laptop there. There we are. Right, here's the next bit. Given instead that triangle OAB is equilateral, express Q in terms of P. So what we're going to start with doing is to draw a nice little equilateral triangle. So let's just draw one first. So here's O. Let's draw point A here. What do I know about A and B? We've got Z is equal to, where's my first point? This, Q minus P squared plus PI, or Z is equal to negative Q minus P squared plus PI. So let's think about the three situations we can have for this thing here. If Q minus P squared is negative, then we get the thing that we just had when they're both on the imaginary axis, right? If Q minus P squared is 0, then both of these collapse down into one point, which is PI. So the situation we're dealing with now is that this is positive, and so this is going to be the real part. Right, so this might be something like 2 plus 3i and negative 2 plus 3i. So let's just see where they sit on my diagram. So the case we're dealing with now is Q minus P squared is positive. So the first one is Z is equal to this positive real number plus PI. So we can whack that onto our diagram here at point A. The second one is the negative of that. So Q minus P squared, negative Q minus P squared, square rooted, plus PI. And we can draw that in on the Argonne diagram, and it's going to sit over here. So that's for the general case. So then we've got this triangle here, OAB. Now, I've deliberately drawn that so that it's not equilateral, but we're told that it is equilateral. So there are two ways that we can solve this problem now, and hopefully this is starting to seem reasonably easy because we've done nearly all the hard work. So here's O, and if we're going to get an equilateral triangle, then I'm going to have one point here and one point here, and I can join them up. That's very bad drawing. There's A and there's B. Right, what do I know about equilateral triangles? I can either work with the lengths or I can work with the angles. So if this angle here is 60, then this angle here is also 60, and so is this one. So doing this first by looking at the angles, if we've got OAB is equilateral, that means that the argument of A, point or the number going with A, must be 60 degrees. right? So that's what we're going to do now. And we've also drawn it that it's in the first quadrant. Okay, so the argument of ZA is equal to 60 degrees. So tan of 60 degrees is equal to the 2 bits of the argument. So we've got P over root Q minus P squared. Remember that first complex number is, what have we got? Root Q minus P squared plus PI. Solving that, tan of 60 is root 3. And rearranging this now gives me the square root of 3 times Q minus P squared is equal to P. 3Q minus 3P squared, squaring both sides, gives me P squared. 3Q is equal to 4P squared. So Q must equal 4/3 of P squared. All right, so that's that question finished, but I'm going to now show you what I think is the easier way, which is working with the lengths. All right, so we know that it's an equilateral triangle, and I can find these lengths here, and they have to all be equal. All right, so I am going very, very slowly on this question. The length AB is really easy, right? Because we know that they're both sitting at PI. So length AB is just equal to 2 times the real bit, right? So it's 2 root Q minus P squared. So that's that one. Now we just do Pythagoras to get length OA. So OA is equal to this. It's the x coordinate squared plus the y coordinate squared. So that comes out to be this. Q minus P squared plus P squared, which is root Q. And it's equilateral, so I know that this must equal this. So root Q is equal to 2 times root Q minus P squared. Squaring both sides gives me Q equals 4 times Q minus P squared. Q equals 4Q minus 4P squared. So 4P squared is equal to 3Q. Q is equal to 4P squared on 3. Right, there you go. I really can't believe any of you are still watching after 13 long minutes. But I think for some of you, this will be quite a tough question. There's a lot of really good complex number stuff in there. So please make sure you've gone through this one carefully, maybe another time in the next couple of weeks. Thanks for watching. I'll have some more questions tomorrow.